Okay, in this lecture, we're going to give some names and hopefully some memorization facts for some common growth orders. Um, so these are the types of growth orders that you'll see a lot, and we're going to make some comparisons, and this would be a good set of facts to memorize because they'll come up a lot. So the key takeaway from this lecture is this table right here, okay? And I've listed a bunch of growth orders, order 1 log n log n squared, n cubed, n to the k, k to the n, and n factorial. And they're common names here. And I do want you to know their common names: constant, logarithmic, linear, log linear, which is one that people often forget. Log linear is n log n, quadratic, cubic, polynomial, exponential, and factorial. And notice that linear, quadratic, and cubic are all special cases of polynomial, right? Because this is n to the k for some value of k. K could be 10, k could be 100, but it could be 3, 2, or 1, okay? A couple of comments here. K in a polynomial is a constant, right? Does not include n to the n, right? That's not polynomial growth. That's something different entirely, which isn't even in this table. And with exponential growth, k must be greater than 1 to have actual exponential growth. If k is equal to 1, then that's no growth. That's the same as constant time. And if k is less than 1, then you get exponentially decreasing growth, which is not typically what you see in the running time of an algorithm. Okay, so memorize these growth orders and this order, because this is the order in which they grow from fastest to slowest, or they're growing from slowest to fastest, I guess. Depends on whether you're thinking about fast algorithms or fast growing functions. Here we have slow growing functions, here we have fast growing functions, here we have fast algorithms, here we have slow algorithms. And remember these names, okay? Now, here's the same or similar information, but put in a more verbal way, okay, and a more ordered way. We have constant, which is big O of 1, is growing more slowly than logarithmic, which grows more slowly than linear, which is growing more slowly in general than polynomial, though linear is polynomial growth just for an exponent of 1. Polynomial growth is always less than exponential growth, and exponential growth is always less than factorial growth. And as we've proven before, if we take a logarithm and we raise it to a power k, that's always upper bounded by a linear function for any fixed k. Now, I want to close this brief lecture by looking at a couple of compound terms. Sometimes compound terms can be confusing. So a compound term is something like n log n, right? We have n, which we understand that, and we have log n, which we sort of understand that. How do they combine? And if you were to compare that with n, if you had two functions, n log n versus n, which one of them grows faster? And there are some quick ways that you can figure this out. So one way to figure this out is to notice that both n log n and n have common factors of n. And so what happens if you divide out that common factor? Okay, if you divide out that common factor, the first one is growing n log n over n is just log n, right? We're left with log n, and n over n gives us 1. So now we can compare log n with 1 and say which of those is growing faster, because we've already divided out the common amount of growth. And clearly log n is growing faster than 1, so that tells us that n is equal to little o rather of n log n. So n log n grows strictly faster than n. And here all we're doing is we're applying the limit of the ratio that we studied in a previous lecture. We're just doing it in sort of a shorthand way. Okay, so one trick is to divide out common terms. Here's one more exercise with this. Suppose we had n squared log of n. So this is not log n, this is log of n, which does occur sometimes. It's more rare, versus n cubed log n. Well, again, we can divide out a factor of n squared, and that gives us log n and n log n. But what do we do from here? There's no more common terms to divide out. In other words, we cannot divide out this log n because this log n is inside of this other log. So this is n times log n, This is not log times log n, it's log of log n, okay? So we can't divide this log n out. That's not possible, it's not valid. We could, at this point, apply a limit. In other words, we could take log of n divided by n log n and take that limit as n goes to infinity. But here's sort of a shorthand way to think about a different way. Common sense will tell us that log n grows more slowly than log n. Why is that the case? Because we know that log n grows more slowly than n. We've already proven that and talked about that multiple times. And why do I say this? Well, because if you were to think about this log and this log, what's inside those logs? Well, this is log n and n. So of those two, which is growing faster, log n grows more slowly than n. N grows faster uh, than log n, right? So log n grows more slowly than log of n. And in addition, so between this term and this portion of this term, log n is growing more quickly than log n. And in addition, we also have this additional factor of n that was mentioned down here. So this portion grows faster than this, and n grows faster than, say, 1 times that. So all of this suggests that n log n is growing much more quickly than log of n. So another way of saying that is n squared log n, which was our original function, is equal to little o of n cubed log n. So these are just some tricks that you can apply, some common sense rules that you can apply to figure out which functions are growing faster than which other functions.